The Biot-Savart Law is a fundamental principle in electromagnetism that describes how a magnetic field is generated by a current-carrying conductor. It establishes a mathematical relationship between the magnetic field and various parameters such as magnitudes, direction, length, and proximity of the electric current. Formulated by Jean-Baptiste Biot and Félix Savart in 1820. This law provides insights into the behavior of magnetic fields around current-carrying conductors. Akin to Coulomb's law, in electrostatics, it serves as a cornerstone in magnetostatics, offering a quantitative understanding of magnetic phenomena.
Hi everyone, this is Reishane Eltanal, and I'll be going to explain to you what is Biot-Savart Law, statement, and derivation. So Biot-Savart Law can be stated as dB equals K times IDL sine theta over R squared, where K is constant depending upon the magnetic properties of the system and medium of the units employed. So I will be showing you what is the final Biot-Savart law derivation. Let us consider a long wire carrying a current I and also consider a point P in the space. The wire is presented in the picture below by red color. Also consider an infinitely small length of the wire dl at a distance r from the point P as shown. Here, r is a distance vector which makes an angle theta with the direction of current in the infinitesimal portion of the wire. Current through the infinitesimal length of the wire is the same as the current carried by the whole wire itself. We can write it as it is also very natural to think that the magnetic field density at that point P due to that infinitesimal length dl of the wire inversely proportional to the square of the straight distance from point P to the center of dl. Mathematically, we can write this as. Lastly, magnetic field density at that point P due to that infinitesimal proportion of the wire is also directly proportional to the actual length of the infinitesimal length of the wire. Theta be the angle between distance vector r and the d direction of current through the infinitesimal length portion of the wire, where the component of all directly facing perpendicular to the point P is dl sine theta. Combining the three statement, we can write it dB times I times dl times sine theta over r squared. Putting the value of constant k, which we have already introduced at the beginning of this SLK. Final derivation of Biot-Savart law.
Good day everyone, good day sir. I am Baclayon Abayon and I am going to report about the Biot-Savart Law formula. Actually, this report is an extension of the previous reporter's discussion and let's talk about it. So, according to the module, the direction of the magnetic field is always in a plane perpendicular to the line of element and position vector. It is given by the right-hand thumb rule, where the thumb points to the direction of conventional current and the other fingers show the magnetic field's direction. So, in this analogy, this pen represents the electric wire, and every electric flow or electric current, there is a magnetic flow or a magnetic current. So, this pen is pointing upwards, and the conventional current is moving towards north or upwards. So basing on the right hand thumb rule, we put our thumb towards the sky or towards the direction of the pen, in this case, or I mean the direction of the pen, or the direction to where the pen is pointing. So if the pen is pointing downwards, so our thumb should point downwards also. Then since it is pointing upwards, our thumb should also point upwards, and then we wrap our fingers around the pen, and then notice that the pen enters the page. So this is the inner page and this is the outer page. So our fingers goes inside, passes through the pen rather, and then goes into the page, and then we wrap around our fingers around the pen, and then my fingers roll into a ball, and then our fingers goes out the page, and that is the right hand thumb rule. Okay, so the module provided us some example problems, and the example problem number 1, we have to find the magnetic field at point P due to the following current distributions, and the module presented two current distributions following the example problem number 1. So the first current distribution is that the fields due to the straight wire segments are 0 at P because DG, S, and R hat are parallel or anti-parallel. For the field due to the arc segment, the magnitude of the magnetic field due to a differential current carrying element is given in this case by, so B is equal to mu naught I over 4 pi, and ds cross r hat over r squared. Mu naught over 4 pi is a constant, or the permeability constant, and then I is the current, ds is the current length element in direction of the current, r hat is the direction from ds to point P, and r squared is the distance from ds to point P. So ds is no, not ds, s is comprised by a specific value, and that value is sine theta minus cosine theta, then cos, then the value of the r hat is negative cosine theta minus sine theta, and then we just have to copy the symbols r squared. So if mu naught over 4 pi is constant, we move I towards the other fraction. We move I into the numerator, and then add r and that I here, and then we add r and d theta, because s and r are both angles. So it's like that, and then we calculate this equation. So we cancel r and r squared, because r minus r squared is r, and then we multiply sine theta to negative sine theta, and negative cosine theta to negative cosine theta. Since negative theta multiplied by negative sine theta is negative sine squared theta. And then negative cosine theta times negative cosine theta is positive cosine squared theta. And since this is a constant, or this is also considered as a number, something like that, we put the negative sign of the sine before the constant, which is mu naught over 4 pi. And then we put it inside the parentheses, and then we copy the I, since r is also is cancelled, then r, and then we move d theta to the after the parenthesis because it is a derivative, and then we put k hat, and then sine squared theta plus cosine squared theta is 1. If we multiply 1 to any number or any variable, the result is still the same, so it's not necessary to put 1. So then d theta r, and then k hat, and copy this, something like that. Then we combine the two fractions together, so we have mu naught I over 4 pi r d theta. According to the module, we remove d theta from the numerator and put it the side of the fraction, after the fraction, and then followed by the k hat. So according to the module, we put b, remove the db na. We remove db from the equation since we already found it. Then b is equal to minus, and then put an integral and put the values 0 as given in the module or given in the example. So pi over 2 can be substituted to d theta. So we replace the values of d theta to pi over 2. So it would be something like this. Then pi 2 k hat. And then we cancel pi, multiply 4 by 2, so it becomes minus mu naught I over 8r and k. So that is the answer of B. So let's move on to the second example problem. Example current distribution. So the second current distribution is that there is no magnetic field due to the straight segments because point P is along the G lines. Using the general expression for dB obtained in A, for the outer segment, we have B. Since it is an outer segment, B, we put out beneath the B. Put out beneath the B, then equals to input integral, and then pi above the integral and below 0 below, and then mu 0 over 4 pi, and then same as here. We replace the r to b because we already it is required because we are finding the values of the b out, and since I have mentioned that r is the distance from ds to point P, and B out, B out is the another like something like another term for the R2, and B out is represented by the lowercase b. So we replace r squared to b. So it becomes like that. And then same process as the first current distribution, we substitute pi to d theta. We have mu over 4 pi. Let's not forget to combine the two fractions together. We have mu 0 I and pi over 4 pi and b. Let's not forget k. And then we cancel the 2 pi's, and the result will be mu 1 over 4b k. There's something's wrong. Actually, it's not supposed to be like this. We combine the two and then remove the theta from the numerator and then put it at the side of the fraction. So we have mu over 4 pi I b, then pi and k. So let's imagine that there is a 1 here, so that we can multiply this one to the first fraction. So we cancel pi, and then 4 times 1 is equal to 4. So we have put it inside the parenthesis, mu I over 4b k hat, and that is the b out. So for b in, we have the same values, but the pi is found below the integral, and then copy the constant 0 over 4 pi, then I d theta, and no, this is gonna be a, and a because it is in, so then k hat, and then we combine the two fractions together. We have mu 4 pi that, and then same d theta, the side of the fraction, and then followed by k. So we substitute d theta by the pi, so it's gonna be replaced by pi. So same procedure as here. We cancel pi and then multiply 1 by 4, so it's the same. Put it inside the parenthesis, pi 4 a and then k, that. And then the module features a negative sign before the parenthesis. It makes perfect sense because it is in, and then the graph features like this. So this is the Cartesian plane, and then there is a graph of the current distribution where there is a first arc going inside the page, or like what I've said earlier, this is the in and this is the out. And in this part of the Cartesian plane is an x, and this is the positive domain of the Cartesian plane of x, and then a negative sign. So did you get it? So the magnetic current goes into the inside the page, and then a second arc, or the B, this is A, this is the B, then and B is going outwards. So if you have difficulty in understanding this, just refer to the right hand thumb rule. So the result for B in is negative mu I over 4A by K hat. And then we are going to find the B net. Okay, so we are going to find the B net, and B net is comprised or is a combination of B out, and B in. So it's basing on the first current distribution, we have negative mu 0 I over 4. We don't have to put the pi here because we already cancelled pi, and then r is replaced by the two variables a and b, which came from b out and b in, and then we put away the two variables and put them and multiply it to the first fraction. So a should have another fraction here, and then b should have another fraction here, and both should be put on the denominator area. And since it is a denominator, let's imagine that there is a 1 above it, as it should be. And then we put a minus sign in between them since a is less than b. Yes, since a is less than b, so that is why we put a minus sign here. And then copy K hat, and that is how we find the B net. And that is all. Thank you.
Here is a given example. A conductor in the shape of a square loop of edge length T is equal to 0.400 meters carries a current I is equal to 10.8 as in the figure. So the problem here is for the letter A, calculate the magnitude and direction of the magnetic field at the center of the square. The formula that we are going to use in here is B is equal to UOI over 4 pi r times cosine delta 1 plus cosine delta 2. So cosine delta 2 is equal to cosine delta 1. And it is equivalent to cosine 45 degrees. And cosine 45 degrees is equal to 1 over the square root of 2. And it will lead to the question B. If the conductor is formed into a single circuit and carries the same current, what is the value of the magnetic field at the center? The formula that will be used is B1 is equal to mu 0I divided by 4 pi times 1/2 times 1 over the square root of 2 plus 1 over the square root of 2. It is equal to mu 0I divided by the square root of 2 pi I. B is equal to 4B1, and 4B1 is equal to 2 to the square root of 2 times mu 0I divided by pi I. It is equal to 2 to the square root of 2 times 4 pi times 10 raised to the power of negative 7 t ma times 10a divided by pi times 0.40 m. Answer is equal to 2.83 times 10 raised to the power of negative 5 t, because you will cancel out the m and a.
Ampere's law was first discovered by André-Marie Ampère in 1826. It is a useful law that relates the net magnetic field along a closed loop to the electric field current passing through the loop. André Ampère developed a law building upon Oersted's and his own experiments, providing an alternate expression of Biot-Savart's law relating magnetic fields and current. However, this law required a specific calculation involving the curl of B, limiting its applicability to steady currents. 4 decades later, James Clerk Maxwell recognized the incompleteness of Ampere's equation and expanded it to include the understanding that electric current gives rise to the magnetic field, providing a mathematical formulation for it.
Ampere's circuit law states the line integral of the magnetic field over a closed path or loop equals times the total current enclosed by that closed loop. Ampere's law can be expressed mathematically using an integral form, where the circulation represents a closed line integral, meaning the integral is taken around a closed loop. B is the magnetic field intensity. dl represents an infinitesimal element of length along the closed loop. Mu0 is the permeability of free space, a constant. I is the total current passing through the surface enclosed by the closed loop. Important notes to take. First, all currents have to be steady and do not change with time. Second, only currents crossing the area inside the path are taken into account. Third, currents have to be taken with their algebraic sign by using the right-hand rule.
So right after we discussed about Ampere's law, its statement, and its important notes, let's now move on to its applications. So the first one is the magnetic field inside a long cylindrical conductor. So a cylindrical conductor with radius r carries a current I. So the current is uniformly distributed over the cross-sectional area of the conductor. So find the magnetic field as a function of the distance r from the conductor axis for points both inside r is less than r and outside r is greater than r, the conductor. So from Ampere's law, we have the closed loop integral of B dot dl equals to the constant mu0 multiplied by how much current is enclosed by this loop. So the integral denotes a closed line integral, indicating we're summing the magnetic field B along the closed loop. B represents the magnetic field vector. dl represents an infinitesimally small element along the path of the loop. Dot denotes the dot product between B and dl, whereas mu sub 0 is the permeability of the free space, a constant in physics, and I, which represents the electric current passing through the loop. So, the magnetic field strength produced by a long cylindrical conductor. So, this conductor is going to carry a uniform current in this case. So, we're going to find the field inside the wire and the field outside the wire using Ampere's law. We will take the Ampere loop to be a circle. Hence, for points inside the conductor, the Ampere loop will be a circle with radius r, where r is less than r. The current enclosed will be I over pi r squared times pi r squared. So, B times 2 pi r equals mu sub 0 I over pi r squared times pi r squared. So, B equals to mu sub 0 I over 2 pi times r over r squared. So, for points outside the conductor, the Ampere loop will be a circle of radius r, where r is greater than r. So, the current enclosed will be just I. So, imagine you have a long straight wire. When an electric current flows through it, it creates a magnetic field around it. So, if we want to find the strength of this magnetic field at different distances from the wire, we can use Ampere's law. So, this law tells us that the total magnetic field passing through a closed loop is directly related to the current passing through that loop. So, let's take, for example, inside the conductor. So, R is less than R. So, if we're inside the wire closer to the center, we imagine a circular loop around the wire. So, this loop has a radius smaller
than the wire's radius. So using Ampere's law, we find that the magnetic field is proportional to the current enclosed by this loop. So as we're inside the wire, the current enclosed is just a portion of the total current. So depending on the ratio of the loop's radius to the wire's radius. So when we consider again outside the conductor, R is greater than R. If we're outside the wire, the loop we imagine still encircles the wire. But now the loop's radius is larger than the wire's radius. The current enclosed is simply the total current flowing through the wire. So right now, we're gonna move on to the second one, which is the magnetic field of a solenoid. So, a solenoid consists of a helical winding of wire in a cylinder. So, it's usually circular in cross-section. So, if the solenoid is long in comparison with its cross-sectional diameter and the coils are tightly wound, the internal field near the midpoint of the solenoid's length is very nearly uniform over the cross-section and parallel to the axis, and the external field near the midpoint is very small. So, we will use Ampere's law to find the field at or near the center of such a long solenoid. So, the solenoid has n turns of wire per unit length and carries a current I. So, from Ampere's law, we have integral B dot dl equals mu sub 0 I end. So, if you're also going to follow the integration path, we also have the integral B dot dl plus integral B dot dl plus integral B dot dl plus integral B dot dl equals mu sub 0 n li, whereas BL plus 0 plus 0 plus 0 equals mu sub 0 n li. So it will be equal to B equals mu sub 0 ni. So, the magnetic field of a solenoid. So, a solenoid is like a coil of wire wrapped around a cylinder. So, when a current flows through the wire, it creates a magnetic field inside the solenoid. So, near the middle of a long solenoid, this magnetic field is nearly uniform or the same strength and parallel to the axis of a solenoid. So, using Ampere's law, to find the strength of this magnetic field, we again use Ampere's law. So, by imagining a closed loop around the solenoid, we can relate the magnetic field to the current passing through this loop. So, other than that, we also have some limitations. So, here in the module, it states here, the limitations of Ampere's law is that it is valid only for steady current. The conventional form of Ampere's circuital law was pointed out by Maxwell. So he introduced the concept of displacement currents or currents associated with time-varying electric fields to generalize Ampere's circuital law even for non-steady currents. So it was this generalization of Ampere's circuital law that played a crucial and central role in the development of Maxwell's electromagnetic theory of light. So, in other words, or in my own understanding, Ampere's law is very useful, but it only applies to steady currents. So, in other words, it works well when the current flowing through a wire doesn't change over time. So, however, if the current is changing, like in the case of alternating current, or situations with changing electric fields, that we need to consider more complex phenomena like displacement currents, which were introduced by Maxwell itself. So these concepts are crucial for understanding electromagnetism and played a significant role in the development of Maxwell's electromagnetic theory of light.